Hi, good to see you all through this social media platform. I'm Aishwarya, Assistant Professor in the Department of Biomedical Engineering, working at Emmanuel Associated College of Engineering. So today I'm glad to meet you with a new topic, RISC Architecture. So let's move inside the topic. RISC means a reduced instruction set computer. That is, it is architecture CPU design philosophy that emphasizes simplicity, efficiency, and high-speed execution by using a highly optimized set of instructions. So RISC is a processor architecture that uses a small, simple, and highly optimized instruction set. Each instruction is designed to execute very quickly using usually in a one clock cycle. So RISC is a CPU design philosophy that simplifies processor instructions to improve execution, speed, and efficiency. The main need of using this RISC architecture, that is the reduced instruction set computer architecture, is faster execution, simple hardware design, reduced power consumption, and better pipelining performance. So this is the RISC architecture where we have the main memory, a data path which is interconnected to hardware control unit, a data cache on both sides which is connected to the main memory. Thus, it reduces the usage of power consumption in a large. So the characteristics are simplified instruction set, load or store architecture, uniform instruction format, large number of registers, pipelining friendly, and fewer addressing needs. So simple instruction set is nothing but it has small number of instructions which is easy to decode and execute. And store architecture is nothing but only load and store instruction access memory. Arithmetic operations are performed only on registers. So these are the load and store architecture. Large number of registers is nothing but it has more general purpose registers and thus it reduces the memory access. Okay. Pipeline friendly is nothing but it has a fixed length format, that is usually it has 32-bit instructions which is faster for instruction decoding. Again, simple clock execution, that is most instruction completes in only one clock cycle. There is no need for going for next clock cycle. A hardwired control unit which uses the hardware instead of microprogramming for faster execution. So this is the one we have seen in that architecture block diagram, hardware control unit which is used instead of, that is the hardware used instead of microprogramming for faster execution. This is the basic block diagram for RISC architecture. That is the controller. This PC unit is connected to program memory. There it is given to the instruction set, instruction register. Then it is used to decode by using a decoder in which the control word is given from the data path, and again the fillback is given from the data path to the next address communication center, so that it is given back to the PC where it is activated or not is done by this RISC. It is done using this RISC architecture. Okay. So the history of development of RISC architecture is there are a number of systems going back to 1960s have been predicted as the first RISC architecture. partly based on the use of load store approach. The term RISC was coined by David Patterson of the Berkeley RISC project, and though somewhat similar concepts have appeared before. The CDC 6600, designed by Seymour Cray in 1964, used a load store architecture with only two addressing nodes. The addressing nodes were register plus register and maybe register plus immediate constants, and 74 operation codes with a basic clock cycle being 10 times faster than the memory access time. Partly due to the optimized load store architecture of the CDC 6600, Chad Donga says that it can be considered a forerunner of the modern RISC systems, although a number of other technical barriers needed to be overcome for the development of a modern RISC system. So these are the authors who have said something about the clock cycle on the RISC architecture and how that is developed into the modern world based on the load store architecture. So this is the basic architecture of RISC. Okay. So according to that, we have seen the basic block diagram. So based on the block diagram, the architecture of RISC is maintained. Okay. So here a program counter instruction memory is addressed. From there, the instruction is given to the instruction register, which is used to reset. Then from there, the output and the register is given to the registers, and the output is given to the arithmetic and logic unit. Again, the memory unit has the memory data input, and the data memory has the memory read and write data input with the data output, which is given to the ALU output of multiplex operator. And also the memories are assigned with the clock and reset of the PC, that is program counter. Again, to the control unit, it is given to the output. The output is given to the arithmetic logic unit and also to the control unit through a common bus channel, where the register are also given back from the instruction registers to the register, and also the feedback of control unit to the registers. Okay. The components of the program counter PC, instruction register area, register file, arithmetic and logic unit ALU, control unit, and memory. So the working steps here, it fetches the instruction first, then it decodes the instruction. Again, it reads operates from the register. It executes operations after decoding and then write the results back to the register. So these are the common instructions happens in the RISC architecture. So what is actually the pipeline in RISC? The RISC processor extensively uses instructions pipelining. Five pipeline stages which are used here are instruction fetch IF, instruction decode ID, execute EX, memory access none, and write back WD. So these are the 5 basic and main pipeline stages. From this, we can also say that one, the pipeline stages are used because they have higher throughput, faster instruction execution, and efficient CPU utilization. Why? Because of this, we are used efficient. So for an example, there are 3 instructions. First, the IF fetch. First, the fetch instruction is given, then the decoding instruction is given, so the fetch moves to the next instruction too. And then the execution is given, so it moves forward. Then the memory entry is given, and it is used. Then the write back is given, so it moves one word forward. So each instructions, when they are given for the each cycles, they will move one step forward so that there may not be any overcoming or overwhelm of the situation. Okay. So this is the RISC design philosophy. There are simple instructions, fixed instruction length, load or store architecture, or pipeline friendly. So what is simple instruction here? There are fewer instructions. Simple instruction, fewer instructions. Fewer means very few, very some. Some instructions each executing in one clock cycle, and that is called the simple instructions, which is the philosophy of the basic RISC design. Then the second one is fixed instruction length. It is easier to decode and pipeline. That is the decoding process is very easy and it is easy to get the pipeline structure architecture. Next is load or store architecture. The load or store architecture is nothing but only the load and store instructions can access the memory which is used in the RISC architecture. All the memory which has to be used for the RISC architecture should be only accessed from the memory through load and store instructions. Pipeline friendly is simplified instructions allow parallel execution. Simplified instructions which allows parallel execution. That is called as the pipelining friendly. So the advantages of using this RISC is the fast execution due to simplified instructions. Fast executions due to simplified instructions. Easier hardware implementation. Efficient pipelining leads to better overall performance and scalability for embedded systems and mobile processors. Some are high processing speed, easy instruction decoding, efficient pipelining, low power consumption, simple processor design, large number of registries, and high performance per watt. Okay, these are the main advantages of RISC architecture. So this is the comparison between RISC and CISC architecture. Already we have seen CISC architecture. Now we are seeing about RISC architecture. So the instruction set in CISC may be few and single, but in CISC it is computerized. The instruction set may be many and complex. The execution time is usually one clock cycle, but for CISC the execution time is multiple cycles. The memory access is for RISC only load or store instructions, but the memory access for CISC may be many instructions access memory. The pipelining technique in RISC is very easy as we are seeing here, but it may be difficult in easy CISC. See, this is the block diagram for RISC versus CISC. Okay, basic program memory, IER instruction is just given, decoder, then it is given to CW data path memory versus CISC. PC program memory and main PC, main PM, then it is going to data path to the data memory. So this is the difference between the CISC and the RISC architecture. So now we are seeing about the RISC architecture where you can say that PC, and then from the data from the PC is given to the program memory, then it is given to the instruction register set, from there it is given to the decoder, from there it is set back, so that it is given to the data path which is flowing to the system, and then from the data memory, the memory file is stored to the data path where the programs carries on. Okay. Examples of RISC processes may be ARM architectures, MIPS processes, and sparse architectures. So now with the sparse. The ARM architectures are widely used in smartphones and IoT devices. IoT devices is nothing but Internet of Things devices. So for that devices and mobile phones, the widely used one of the chip is called as ARM architecture. So MIPS processor teaching and embedded systems, it teaches and uses the embedded systems research. Sparse architecture, high performance computing applications. Sparse means high computing, high performance computing applications. Sparse architecture means High performance computing, high performance computing applications is called as RISC architecture. So this is one of the example of our architecture. Notice here, there is for this advanced microcontroller bus is used. So it has all the external power and external power. Then a DIC is given where the external bus interference is interference with a bridge in between the ARM bus interference is used. So the output and the reset button is also rapidly fixed down with the ARM. A decoder on the on-chip primary is also used, which is called as the system bus. And then the peripheral bus has timer, power system, and input control. So AMBA is nothing but advanced microcontroller bus architecture. APK is complete advanced microcontroller bus architecture design kit. ACT means advanced microcontroller bus architecture compliance test bench. The prime services used here is ARM's Tampa compliant peripherals. So this is the one of the example for RISC architecture. So this is another one, microfit user. That is, it has a two-wire debug. That is a two-way AT jack, which is debugged or fortified to the breakpoints of the photopaste with the countless samplers. And then it is given to CPD, that is the 8 cells, which is given to the execution unit, and the arithmetic logic unit has the DSP access, which is given to the MCU access of IEEE format, and then it is given to the enhanced MTU and DSP access. And the MSU has input or output files, which has given from the decoder about with the MIPS 32 chip. Then with the DSS data, the system control code from the CPU should be given or taken as a bidirectionally for the system input and forward. So the one cache controller is given to the M1, which is given to the D controller. I cache is given to the D controller, where it is called as the power management system, so that it cannot be changed to any alternatively with any of the exclusively to the M5150 cache is used here. Again, the D cache controller is given bidirection to the D cache, and then it is given to the binary input output unit transfer. Also, from the iCache controller, it is also connected with the iCache. So all these were connected to the system bus, which is connected inversely in the DI, that is bus enterprise unit bus control bus. So next we have this pass-through level architecture is another related example for the RISC architecture. So nothing but it has the user up to unit and power user. So here you have given three. From the three they are given the from the three users they are given to the consumption schemas. There is starting. And step to get to enter from the internal stream, and then it is given to the data analysis. So it was nothing but the viewers are considered as the external level from external level, and the consumption schema is considered as the consumption level. The internal schema is considered as the internal level, and the database is considered as the physical data organization. So organizing the data important thing at this time. Database management using the physical station. So the main real-time applications are smartphones, tablets, embedded systems, IoT devices, automotive electronics, networking, equipments, consumer electronics. So all these are the applications of RISC architecture. The reason mainly used here in order to put that the RISC architecture can be widely used in many types in this manner. Involved so that the real-time applications can be implemented easily without any delay or problematic features. This is a best examples of the real-time applications of RISC architecture tools. Next generation context that is used to can be used for any type of smartphones. That's when topic 62 is going to chapter 6. Then it is the next topic 6 that is very new and also updated form. That is next generation on 46 is the next on 46 700. If you is refreshed from refreshed. 46 it is updated to dynamic shared email, that is DSP. So this is the first example for that. I will say some process using the RISC architecture based smartphone development. So another one example which we can see that is a network device is nothing but how they will utilize this albeit bridge space. So these are used for that. Used as a network devices in the RISC architecture to maintain that constant learning. So this is for another one, the high performance computer, which is personalized medicine, machine learning, high performance data analysis, high performance trading, computer aided design, data center and network optimization, autonomous vehicles, personalized medicines. Everything will come under the performance computing devices. So all these were used as one of the advantages in the real-time applications of RISC. So how does RISC used in every terms and how it is different properly. So next one is the embedded electronics, which is used in embedded software and hardware development. Software development, which is equivalent to software simulations and verifications. Again, the embedded electronics uses system integration, validation, also the manufacturing and production of large unit like automation. Okay. So the examples include on-the-based processing and silicon processors are used in the CPU for many types of robotics and experiments. And then the complexity instructions it is made for RISC and design process. So it has both instruction length with the memory accessible stored and also has large number of registers, execution time, which was mostly 1 to cycle, and the control device hardware. Also the complexity is simple with the easy pipeline, that is the RISC architecture. But and so there's a RISC architecture, but this is large instructions that is variable instruction length and direct memory access is used for memory access and also for registers. If any registers are used to run from register using an execution time must be on the site is not RISC. Also it is microprogram, also it is microprogram analyze like that of that. It is calculated to the RISC is microprogram. Also, the RISC is complex in nature, but it is simple in nature. The pipelining scheme is very easy for RISC, but it is contrast difficult RISC. Okay, these are the comparison between RISC architecture and RISC architecture. Okay. So conclusion, in the conclusion section, to say something about RISC architecture, that is nothing but RISC-based sequence instruction set instruction with sensor and secret cryptic is fixed learning instructions including the deep theory. Hence, the lowest architecture uses memory operations, picking the log register set improves performance. Because register set improves performance. So pipeline increases processor speed, pipeline increases the processor speed. The RISC is widely used in modern embedded and mobile systems. Thus, many Europe using the RISC in the comfort because it is not used in the system as we all know mobile systems is very fast. Nobody makes use of mobile system communications and now it is covered in the 5G communications and also it is can be connected to any of the embedded systems which is acting as the hardware of the systems that used as the mobile systems, that is the architecture can be used in this type of advantages. application. So in summary, maybe there is emphasizes simply the speed, efficiency, principles with more processes achieve performance while maintaining low power consumption. This guides is there's low power consumption. So the future outlook of this architecture is maybe it continues to dominate mobile and systems due to low power and high efficiency. Due to low power, so this is very low power for using both the hardware and software under the development of mobile systems, and also it effectively reduces the usage of power supply, so it reduces the power. So I hope you all understand what about the main basic concept of RISC architecture, and also do you like the video, comment if you have. Thank you for watching. Thank you.